Today I am going to start the new chapter of fluid mechanics. The chapter is hydrostatics. That means here fluid will be at rest condition. It will not be moving. So in the very beginning, the first topic which will be discussed is Pascal's law. So you have studied this law in class 7 or 8. What is that law? The law is pressure at a point in a fluid at rest is same in all directions. Here I have written this one. Pascal's law. Pressure at a point in a fluid at rest is same in all directions. You have studied experimental proof of this law. Now today in your BTech first year course, second semester first year course, you will learn the theoretical proof of this law. So I am going to prove it theoretically. First you choose the coordinate axis. So I am choosing this to be the x-axis. Here x-axis is taken to be horizontal. This is the y-axis, and in the perpendicular direction, perpendicular to this page, is the z direction. Okay, I am not drawing that one. Now take a fluid element by drawing a straight line like this. This is the origin O. This line cuts or intersects x-axis at point A, y-axis at point B. Okay. So OAB, this is like a triangle, and suppose the fluid element cannot be two-dimensional, so it must be three-dimensional. Any object is three-dimensional. So you assume the length OA to be delta x. Okay, the length OB to be delta y, and in the perpendicular direction to this page, that is in the z direction, you assume the thickness to be delta z. Here delta x, delta y, delta z all are very small. You know, whenever the sign delta is used, the quantities are very small, and they are not same. They are very small, but they are not same. Now you consider that on the edge OB there is one area. Okay, thickness was taken to be delta z. So you will get one rectangular area on OB. Suppose on that area the pressure is uniform and it is denoted by P suffix x. Why x? Because it is in the direction of x. That's why Px. Similarly, pressure on the rectangular area OA, here OA is the edge. On this edge there is one rectangular area like this. Okay. So suppose here pressure is denoted by Py. Right? Y means in the direction of y. It is parallel to the y direction. That's why y is taken. Now since the fluid is at rest, one more thing. One edge is left, that is AB. On AB there is one also rectangular area. On AB the pressure, which is perpendicular to the edge AB, is denoted by Pn. N for normal. P suffix n. N for normal. Okay. Now under the action of these pressures, the fluid element is at rest condition. Previously it was mentioned that it is a chapter of hydrostatics, and here the fluid will not be moving, it is at rest condition. So under all these pressures, the fluid element is at rest condition, it is not moving. Therefore, you know that the resultant force on the fluid element must be 0. Okay. So resultant force, say it is denoted by F, it is 0. That means we are going to resolve this force into two components, along x and along y. Okay. So since resultant force is 0, that means sigma fx is 0 as well as sigma fy, this is also 0. What is the meaning of sigma fx? Means resultant in the direction of x, that is 0. Resultant in the direction of y, that is also 0. So first we are considering the direction x. Okay, x direction. We are considering this. And I have previously mentioned that x is taken to be the horizontal direction. So here x and z both are horizontal, but y is vertical and it is in the upward direction. Okay. Now what are the forces which are acting in the x direction? First consider the force due to pressure Px. Here what is the area on the edge OB? It is equal to delta y, this length, multiplied by the thickness delta z. Delta y into delta z, that is the area. And pressure is how much? It is Px. So force is Px multiplied by the area delta y into delta z. Then consider the force Py, pressure Py. Here there will be no contribution of Py in the direction of x because here y direction is perpendicular to x. But there will be one component of Pn in the direction of x. What is that component? So first you draw a horizontal line from here like this, okay? And suppose this angle, the angle OAB, this is taken to be theta. So since this is theta, that means this angle is also theta, okay? Because this line OA and this line are parallel to each other, so this angle and this angle are same. So this is also theta. That means this angle is how much? This is 90 minus theta. So if you draw one vertical line from here, so this angle will become theta. Okay. So what is the force on the edge AB? Actually on the surface, rectangular surface, which is on AB. It is equal to Pn multiplied by the area on AB. Area on AB how much? First the length AB. Length AB is root over of delta x square plus delta y square. Okay. So this is the force. Okay. So this component will be how much? Multiplied by cos theta. And this component in this direction, the component will be the same thing multiplied by sin theta. So here our requirement is to take this one, that is component with sin theta, and it is in the opposite direction of x. So with a negative sign we have to write this one, minus Pn multiplied by this into sin theta. Okay. Is there any other force along the direction of x? No, there is no more force along the direction of x. So this is the summation of forces along the x direction, and this must be 0. Okay. So this is equal to 0. We are writing. Now, what is sin theta? Sin theta is equal to OA divided by this hypotenuse. No, sorry, OB divided by this hypotenuse. Okay, that means delta y Px multiplied by delta y into delta z. Oh, sorry, one more thing we need to write. That is, here delta z should appear. Okay, delta z should appear because this length multiplied by delta z becomes the area. So Px into delta y delta z minus Pn into that delta z I am writing here, then this hypotenuse, then sin theta. Sin theta means delta y divided by this delta x square plus delta y square, which is equal to 0. Therefore this term and this term are cancelled, these hypotenuse terms. So this becomes delta y into delta z into Pn. Here delta y delta z is appeared here. Now divide both sides by delta y delta z because the product is not 0. None of these two is 0. So product is not 0. Therefore we are getting Px minus Pn is equal to 0. And in the next step we are getting Px is equal to Pn. Okay. Next, we are considering the y direction. Considering the y direction, so first we are using this one, py multiplied by the area. Area is delta x into delta z. So py into delta x into delta z is the area. Then again there will be no contribution of px in this direction. They are perpendicular to each other. But this component, this vertical component we have to take, and this is opposite to the direction of this py. So with a negative sign we are writing what will be the component? Pn into the hypotenuse into the thickness delta z, which makes the area, multiplied by cos theta. Okay. And one more component will be there, one more force will be there. That force is the weight of the fluid element itself, and which is acting in the vertically downward direction. So with a negative sign we have to write that thing. What is the force? Let us consider the thickness, the density of the fluid element to be rho. So what is the weight? It is mass into density. Mass is how much? It is density multiplied by the volume. What is the volume? Volume is half into the area of the rectangle triangle, that is delta x into delta y, multiplied by the thickness, that is delta z. So this becomes what? This becomes the volume multiplied by rho. This becomes mass multiplied by g. So it becomes weight. Here again we are replacing cos theta by the delta x divided by the hypotenuse. So py delta x into delta z minus under delta z should be outside the under root sign. Okay. So Pn into delta z into this delta x square plus delta y square multiplied by delta x divided by the hypotenuse and minus half rho g delta x delta y delta z is equal to 0. Now divide both sides of the equation by delta x delta z. So we are getting py minus pn, and these two terms are again cancelled. Okay, py minus pn and delta x delta z goes, so remaining term is half rho g into delta y minus half rho g into delta y. Now we know that here rho g, these are finite quantities, py pn also finite quantities. So but delta y, this is a very small quantity, this approaches 0. That means if you take the limit, the contribution of this term will be 0. Okay, contribution of this term will be 0. Therefore ultimately we are getting from here py is equal to pn. Okay, earlier we have got px is equal to pn, and here we have got py is equal to pn. Therefore ultimately what is the result? Result is px is equal to py is equal to pn. Now delta the direction x and direction y were our choice, but the direction in normal to the hypotenuse, that was not our choice. Now you know the angle theta, which is represented by OAB, the angle theta, that depends upon the length delta x and delta y, and those lengths were taken to be very small, but they are not equal. That means theta may have any value. Therefore pressure in the direction of x, pressure in the direction of y, and pressure in any direction, it is independent of the angle theta. Okay, so all they are same. You know that when the length delta x delta y, they are approaching 0, that means the triangle or that fluid element shrinks to a point O. So we can say that at the point O, pressures from all directions are same, and that was Pascal's law. So this is the theoretical proof of Pascal's law. Okay, fine.